Hey, sound check. Hey, sound check. All right. Um, Sorry for the late start. I tried to increase the output resolution and my either my internet or my GPU can't keep up with it. I'm assuming my internet. Um, so I got to 720p, but I tweaked some things that should hopefully improve. Um, so yeah. Um, Maybe the video quality will be a little bit better. I don't know. All right. So, skipped a few weeks, mostly because I was getting distracted by various things. Um, where we left off, we had gotten um, some mostly good abstractions written around GPU buffer handling and different views for buffers, which is good. Um, the let's see, the next step is for us to do similar for textures. We're not going to go ahead and do the full texture implementation because I don't want to deal with like loading textures from disk and computer MIPS and all of that nonsense all at once. But we do need some amount of texture handling and being able to bind textures as shader resources and etc. Um, Otherwise, we don't have any way of doing multipass rendering. So that'll be most of today. I also want to get some handling for swap chains that is a little nicer. And in particular, I want to handle swap chain resizing, which currently is not a thing. You create a hard-coded 720p swap chain and we leave it there, which is not great. Um, so that's what we're going to do today. Before we get started, at this point, I think it's useful to take a step back and talk about where we're going with this. Because if we run our engine, our demo right now, like rendering things, we've got an object, it's lit by its own light. What more could we want, right? So obviously this is not a production quality renderer, but it's useful to think about what we're actually missing. So there are a couple of different, I don't actually know what the correct term for this is, but like archetypes of how to structure renderers. And specifically how to structure renderers that use some form of like physically plausible lighting. Once you get into the realm of oh, everything is sprites, or oh, everything is toon shaded with outlines and all of that, you can get into some weirder renderer designs. But the focus of this project is physically based lighting. So that's the sort of engine design that we're going to go for. So when I talk about archetypes, I'm talking about like forward rendering versus deferred rendering versus visibility buffer, pass. So it's worth thinking about like what is the actual, like, what's going on there? What are we doing by picking a forward renderer versus deferred renderer versus viz buffer versus whatever, right? What are the actual differences? So in terms of a physical lighting model, there are really like three primary components to rendering. There is visibility, which is, for a given pixel, what object does it see? What objects does it see? Because see multiple. That's the critical thing to know. So in real-time renderers, we handle that with rasterization. You can also handle this portion of things with ray tracing, or I can't spell visibility a bit. And so on. Like, visibility is just figuring out what objects cover what pixels. So for us, that's going to be the actual rasterization process. Then there is materials. So this is stuff like what color is an object, what direction is the surface facing, how rough is the surface. This is the surface a metal or a dielectric, or something weird, like there's something outside of that boundary. So this is your albedo, your normal maps, your just general material properties stuff. This is where all your material textures come in play, right? Just what material is this? And finally, we have lighting, which is obvious, I guess, for all the lights in the scene. How do those lights interact with the material, and what is the output, I guess, the irradiance from that surface under this pixel. So the difference between the various render archetypes is how you handle these three steps. So, for example, in our existing render, our existing render is basically as close to the ideal forward renderer as possible. We do a single render pass directly to the swap chain. We do all of our visibility, material, lighting, and post-processing in the same shader, right? So there's this idea that forward and deferred are diametrically opposed things, but not. It's not your forward or your deferred. There's a continuum of options between the two, based on what portions of these, what components of the rendering you want to actually defer. So I guess let's talk about that a bit more concretely. So then forward is basically everything in a single shader. Your more standard gbuffer style deferred renderer, so equivalent like Unreal, I guess, puts a split here. So you have your visibility and material get evaluated in your debuffer pass. And then you have a separate lighting pass that comes after that. We can also structure things like this, where we have prepass that determines visibility, what object is under each pixel, and then we have a second pass which does the material evaluation and lighting. This is the classic version of a visibility buffer renderer, which has a lot of really interesting properties. Being able to get wasting significantly less work when you're doing your really expensive lighting shader. For reasons I'm not going to get into right this second because it's not relevant. You can also do this. You can have multiple breaks here, right? So Unreal 5's Nanite renderer sort of splits all of these into separate things. So it has a visibility buffer for its rasterization, and then it has a material pass that turns that visibility buffer into a standard G buffer, and that fits it into its existing lighting code. Same lighting paths that exist in UE4. So the point I'm making here is that forward versus deferred is not really the end of the story. It's how do you handle, like, how do you factor apart your visibility, your material, and your lighting? So the target that we're going to look at for this project is a standard gbuffer deferred renderer. So we do a gbuffer pass that does visibility and material evaluation, and then a screen space lighting pass afterwards. I considered doing a visibility buffer style thing, but visibility buffers are complicated to implement for various reasons that aren't a lot of fun. And having a gbuffer around is very useful in terms of just extra options it gives you that forward or traditional visibility buffers don't give you. All right. So there are other options beyond, how do you split these apart? Like, this is the biggest part of designing a renderer, but there are more decisions to be made. So deferring work sort of relies on the assumption that you have one surface per pixel. Right? So every pixel only sees one surface. And that's fundamentally not true, because transparent objects exist. So you actually have some options on how to handle this. The only option that really makes sense for a real-time renderer is you tack a forward pass onto the end of your render pipe to handle translucent objects. I guess the other option for real-time is you don't have translucent objects, which is a choice you can make. It is not a choice that makes, you will not make a lot of friends with artists by telling them that they're not allowed to make anything transparent. Other options that are a little bit more out there, so you can do something called depth peeling, where you do an opaque render of the scene of all your objects, including the transparent ones. And then you do another render and you discard any surface that existed in your first render. So you get like the second surface of the scene. And then you can do that again for like the third surface or the fourth surface or whatever. That's actually a really cool technique because it gives you full information about the scene, which gives you options for things like, hey, I want to implement post-process depth of field and I want it to be correct, which is not possible in a standard deferred plus forward renderer. So that's interesting. But the downside to that, of course, is that you have to render your scene n times, and you may or may not, you have to have a fixed number of layers because you don't know how many layers you're going to need. So you may end up wasting work when there's really only like 2 layers to the scene, but you're rendering 8, right? Or maybe you're in a complicated space where you really need like 16, but you're only rendering 8, so you miss a lot of the details behind that. So in general, that's not an approach that real-time renderers take very often, just because a lot of the artifacts that come up from doing forward translucency are things that artists can work around, and you can't really you can't make translucence a whole lot faster than just a single forward pass. So the technique we're going to use to handle translucence is, for most of the stream, we're going to just not have anything that's translucent, and then eventually we will tackle on a forward-only pass for translucent rendering. Let's see, is there anything else worth mentioning? I guess going back to the architect discussion, Given that deferred renders let you do cool stuff faster, so you can technically do screen space reflection in forward, but you lose out a lot of your opportunities for doing it well and doing it fast, right? But in a deferred render, well, that's just a thing that you can do really fast in deferred. And there's a variety of other things. Basically, anything that is like spatially dependent lighting works better in deferred than forward, because you can do, like, you can look at material evaluation for adjacent pixels as well as your own. So given that, why would you ever want forward? Well, the issue is that deferred renderers have to write out a gbuffer, and gbuffer is, depending on how flexible you want your renderer to be, can be, 4 or 5 textures, and that's a lot of bandwidth. But in exchange, you have shaders that are relatively small and self-contained, because material shader is over here and your lighting shader is over here, and you don't have to deal with the register pressure implications of having them be in the same shader and the compiler having visibility on both and doing terrible things because you hit some complexity threshold or whatever, right? But forward has the advantage of not needing to hit the texture unit very hard. That's actually really useful in terms of scalability, because in general, making ALU faster on hardware is easier than making bandwidth faster on hardware. So between 2 generations of GPU, you're going to get a lot more ALU available, and you might get a little bit more bandwidth. So the growth curves of those two are very different. And so a forward renderer might be relatively slow. It's doing a lot of math in a single shader. So you get bottlenecked on register pressure and whatever, so you're not using the full GPU. But it is very likely that the next generation of GPUs is going to add more shader cores for you, and forward just happily eat them up, whereas deferred is going to bottleneck on bandwidth and stay bottlenecked on bandwidth, and it may not get as much improvement over time. So there is a performance reason to go for forward, which is just in the long term, scalability is going to lean towards forward rendering rather than deferred, just because bandwidth does not increase as fast as ALU. There are other reasons that forward can be better, having more flexibility in your shading model. I can handle anisotropy well without having to figure out how to store a tangent basis in my gbuffer, which is nice, right? That's non-trivial. But in general, at the moment, we are sort of at an impasse where forward and deferred are pretty much the same performance, or they can be the same performance depending on the details of what you're rendering, how you've implemented each of them, what hardware you're running on. But as time goes on, as shader cores get, as GPUs get more shader cores and bandwidth stays the same because making memory faster is hard, I think you're going to find that forward gets faster than deferred does, if that makes any sense. Okay, so enough rambling. We are going to have a deferred renderer in this engine, not necessarily because it's the best option, but because it's the one that I haven't written before, so that's what we're going to do. So in order to support a deferred renderer, we by definition have to have multipass rendering. Because the entire idea is you render out the gbuffer and then you have another pass that has to do the lighting on that gbuffer. So in order to really support that, we need to have the capability in the engine of creating arbitrary render targets, having a pass that writes to them, and then having another pass that reads from them. So at the very least, we need to have render target views and texture SRVs set up in the engine. We actually also need the ability to bind our render target as a UAV, because deferred lighting typically works as a compute shader for reasons we will get into. And for a compute shader to produce an output, it has to output to a UAV, because there is no standard render target functionality available to compute shaders. So all of their rights have to be explicit, which means that we have to have a UAV. So that is why we are going to go ahead and implement the ability to create GPU-only textures and bind them in various ways, because otherwise we can't go ahead and start building this renderer. What we're not going to do today is we're not going to handle like asset textures, where you will load a texture from disk, do some pre-processing on it, and put it in the GPU memory so that you can read, your albedo texture or your normal map or whatever. We're not going to do that today, mostly because I don't want to, and that's going to take a long time. All right. Enough talking. Let's go ahead and get started. Right. The other thing that we have to handle is, you'll remember last time at the end, I believe, I sort of cheated and decided not to handle the per frame, rather per pass resource binding correctly. So we do need to handle, creating or updating our per frame descriptor heap and copying descriptors into it, and to do our descriptor table bindings. I have some ideas about how that should work. It shouldn't be too terrible, but we'll see. All right. So we're actually going to start with the descriptor table thing because it's going to be important. So the annoying thing about how DX12 handles descriptor bindings is that all of your bound descriptors for a table have to be linearly contiguous in a descriptor heap, which is kind of annoying, and will get more annoying with assets when we get to the point where we're just sort of willy-nilly allocating descriptors out of our heap out of our storage heap whenever we create textures. So there's not going to be any rhyme or reason to the inputs of our descriptor bindings, because it's impossible to optimize that in all cases. So imagine you had a case where it's like, imagine pass 1 binds A and B, pass 2 binds B and C. You can handle this by laying things out as A, B, C, and then you pass offset 0 and then offset 1, right? But then you come along and you have pass 3, which does A and C. And well, in order to support this, A and C are separated by B, right? B is in the middle, but this pass doesn't expect that to be the case. And so you would bind the wrong descriptor here. So we can't just rely on, well, we'll put things in the storage heap in the correct order, because there may not be a correct order that is globally correct. So instead, what we will do is we'll have a per frame heap, and we will just copy in the descriptors for each pass. So we would have AB, and then BC, and then AC. And then we can just pass offsets into this table for each bind, and we would get the correct results. In theory, you could do things like, hey, the prefix of this pass matches the postfix of this pass, so we don't actually have to double up on the B here. But it's really complicated and doesn't save you a whole lot of memory, so I'm not going to bother. So what we need to do is we need some structure that can tell us, hey, here's a here's the set of binds for this descriptor table. All the slots. And then we need to know like what heap it's supposed to go into. So we have two options. We have like the general buffer resource heap, and we have the sampler heap. So those two separate heaps, and we will have to manage them separately. And so we need to then have a function call where we bind one of these descriptor tables, which goes through and copies the correct descriptors into our parframe descriptor heap and update and tells the command list about what's the pointer that is used here. So that should all be relatively straightforward. I'm making an assumption here, which is that we can update the descriptor heap, like add more entries to the descriptor heap while it's in use by other by rendering, as long as we don't like change descriptors out from underneath something that is rendering, like we can add more to the end. I'm hopeful that's the case. If that's not the case, then we're going to find some really interesting problems. But I hope that won't be a problem. We can also take this opportunity to like build some structure around setting up our root signatures. I'm not going to bother with that right now. But a thing we can do eventually is, hey, set up, we should have some knowledge about what our root signature structure looks like, some knowledge of what types we are binding for our descriptor tables, and then some checking, say, hey, you bound a texture to buffer bind, are you sure, sort of thing. Or you give me an SRV when you're supposed to give me a constant buffer, this is going to cause a problem, sort of thing. But for the moment, we're not going to deal with that because I don't want to, frankly. All right. I want to wrap our descriptor heaps just because we're going to have to track this count a lot, and I don't want to have to deal with that everywhere. So we need, just go with me here. Also keep track of our capacity so we can yell if we exceed it. And I think that should be sufficient. So we can have a GPU descriptor heap. We need that for our per-frame heaps as well. Let's see. Alternative descriptor type, I believe. And the capacity. I have my connection on. So we can create them, we can destroy them. Um, can allocate one, or we can allocate a descriptor handle out of it. So allocating CPU handles enough. Let's see. Yes, I think if we can always get back to GPU handle from the CPU handle if we need to, but I don't think that we ever directly use GPU handles on the CPU, which makes sense. So that should be fine. Just need to be able to reset the heap. So this is per frame data, so we have three sets of per frame descriptor heaps, and so at the start of the frame, when we acquire that frame, we're just going to reset its descriptor heap, which should be safe to do because we already guarantee that the previous version of that frame has retired before we use any of its data. That's why we're triple buffering. Should be fine. And that way we don't have to like create one of these every frame. We can just reuse the existing ones. So these should be relatively easy. Right. We also need to know if we're creating a shader visible heap or just like a storage heap. So that's important. Seriously? Fine. Enums are just integers. Like, you're not actually making it better by not letting me cast an integer to a enum implicitly. Ugh. All right. Okay. I need to set some of this result as well. I keep count to 0. Capacity. Assign heap. All right. Military car that destroys. No. Okay. Should probably do that actually. I should probably make destroy null safe. don't feel like fixing it right now, so we're going to do this. Um, Also, none of my none of my destroys actually free the objects that you create. That's not great. Hey, that's what all the leaks are from. I think in order to do that, I actually do need to not check heap. We'll fix the other stuff later. Now I need to allocate from the heap, which is this code. Heaps need to store off the type. Right. Alright, that's good. And we say at this point we need to keep set its allocated count to 0, and that should reset it. I assume that this is fast. We could compute this once when we create the heap. Like we could call this once when we create the heap and cache it. I assume that this is just. Like, I don't know. Do we have visibility of the definition? No. I don't know. If it shows up on a profiler, we will make that not do that. Let's see. Should be everything we need to do with heaps. Now, all of this other codes, I'm happy. There's this. Let's see. Oops. You would think, for having a job that's all about typing, I would be better at it, but I'm not. So our output destroys don't take the context, so All right. Check that we actually compile now. We do not. Take context into a lot of calls that don't necessarily need it just because, like, I don't know, I feel like it's always better to have access to your global data structure, even if you don't need it yet, just because it's a lot of work to go and plumb that back through the API if you decide you need it later. It's usually useful. Okay. Do we build now? We do. Do we run correctly? No. Right, because now we no longer create the storage heaps as shader visible, which means that we have to handle the descriptor binding stuff first. Sorry about that, folks. How do I ban you? Do I not have that option? Yes, I don't have that option. Okay, well. Apologies, folks. Okay, actually, let's just look this up. I'm not gonna bother with that anymore. I will delete things as they come in. Maybe. this point, I think I'm just going to end up turning off chat in general. Can I do that at this point? There we go. All right. Not like anybody watches these streams. I don't understand why they bother spamming them. Okay. So we need to have some idea of binding descriptors. Let's see. So, this is off of GPQ. Let's see. Just need to know the descriptor types. This is not the long-term solution here, I don't think, but it'll get us unstuck. So it's getting long. Context, device, coffee, descriptors. Interesting. We got different ranges for each, for the destination and source, which is really useful. We only need one range for destination. One. The destination side, and then source side. For now, we're just going to assume that all of our all of the pasta and descriptors are discontiguous. We could, it would not be too difficult to like identify subranges and stuff like that, but I don't want to bother right now. Because this is marked as optional. I kind of wonder if I pass null here, it would just assume all of these are size 1. Worth a shot. All right, so Pick the heap that we need. Allocate one. Actually, we want this to be. We want this to take a count, and then it returns. If it allocates a range. All the existing calls need to be updated. But this is nicer anyway, because general rule is you never have one thing. You never allocate one thing. You should always be block allocating anything small. This also needs to take the command list because it has to do. The command list to actually bind anything. course, this needs a GPU descriptor, right? Okay, we're gonna do something incredibly hacky just to get it to work, but say minus, let's see, actually no, we can just pull this off here. Mhm. This is not awesome. We should probably have some wrappers around descriptor handles so that we can like just have, here's the CPU handle, here's the GPU handle, and not have to deal with that as much, but it's fine. Do need this before we can do that. Let's see. Yeah, that doesn't actually matter. You're not going to have more than 4 gigabytes in a single descriptor heap, so this one doesn't matter. All right. So we can do GPU Q set or find descriptors, context. Zero. Block builder. Super list. What, like 3 or something? Um, vertex data and camera data. Is that it right now? Yeah, that's it. Right. Descriptor heap. Right. I wonder if I can just do this when we get the command list, because that's within Q, so we can just do things like that, I believe. Let's try it at least. So, result set descriptor heaps, 2 of them now. DX12 script. All right, moment of truth. Did that work? No. That's interesting. We're not creating a sampler heap. That's right, we aren't. The other thing is we have to reset we don't actually have context here. Okay, so I guess reset doesn't use context, so it would be nice to have it around. We can just not. So we can reset. Buffer descriptor heap and sampler descriptor heap, which we need to do, otherwise we're going to just like continue churning through the descriptor heaps, and we will eventually run out of descriptors, but we can just reset them and reuse the existing stuff. I think that might be it. Hey, look at that. We are handling bindings closer to correctly, and we have our teapot back. That's pretty cool. Of course, I didn't actually have that marked down as a goal, because I never have the things that I actually do marked down as our goals for streams. So, let's see. Everybody behaving, yes. Right, well, we have that. We're now going to go and do some handling for textures. So we can use the texture as a shader resource view, RTV, DSV. UAVs are actually common too. All right. I think that's the full set of reasonable usages for textures. I mean, you can technically do things like render to a texture. Well, no, I don't think you can render to a texture and then reinterpret it as a buffer unless. Yeah, I don't think it's possible. You have to do memory. Yeah, we have same tricks to do that. Whatever. Point being, you're going to have various usage flags. So you can use it as a SRV, a UAV, RTV, or a DSV. Which should be everything that we need to do with textures. So we need our resource. Now, we can use 16-bit integers here because DX12 just, there's an API restriction that you can't create a texture that's larger than 64K in one dimension. Is it 64K? No, it's like 16K. In one dimension is like the maximum dimension you can use. So there's no point to put that in a 32-bit int. Let's see. We're never going to map these. Can't. I mean, I guess technically you can. But you never want to put a texture in your upload heap that's wasting upload heap. Is it? Yeah, it's here so we get better alignment. Let's see. It's a whole bunch of stuff with like MIP levels and array layers that are that can be important, but nah, well, we'll go ahead and do it. Width, height, depth, array layers, MIP levels. You actually need to know like the texture dimension. Because you might have like 1D textures, 2D textures, 3D textures, 2D textures with arrays, whatever. Um, okay, this is actually going to be really awkward to do. So instead of having it, instead of passing in all the parameters needed to build a GPU texture in arguments, we're going to have a configuration struct that you pass in. Because when in doubt, just copy Vulkan. Quite aligned. Oh well. Okay, let's. Yeah. That's in config, and it will return the texture created from it. Texture destroy. Finally, we need that's all we're going to create right now. We'll eventually need to create the UAV versions, but I'm not going to bother right now. We also don't need an upload right now because we're not creating asset textures. need a format. Just like the XGI thing, right? Okay. Don't know if that's everything, but it's enough to get started. Layout. think the only time we're going to care about texture layout is one, if we're reading back texture from the GPU to the CPU. So we need to know how it's laid out. And two, when we upload asset textures, because we want to do pre-processing to put it to do block compression and put the texture in the right format so that it's just like a mem copy into the buffer, and the so you have the option of just like putting things in a row major buffer and then doing a buffer to buffer, or like a row major texture and then doing a texture to texture copy to get the GPU to do like the layout swizzle for you, but that's expensive. So nicer if we don't have to, if we can just do that offline rather than doing it at runtime. But for now, we're just going to let the GPU pick the layout because it knows what it wants for more efficient textures. Let's see. So, unlike buffers, we actually have to care about resource flags for textures. So we will use our usage flags to determine what we can and cannot do, and set these flags accordingly. So if our config usage flags usage RTV, if we can use this as an RTV, then we need to allow render target. Same for that stencil. Should actually also check here to do. We should also check that we actually have a valid depth stencil format here. We could do the same for render targets because some types of textures aren't valid for render target usage, but that's a much longer list, so it's harder to check. Usage. Good texture. UAV. Here. Should make these a bit more formalized. Correct, is deny shader resource SRV only, or is it other things? Yeah. So what this is useful for is for like depth buffers that aren't ever read from, because most GPU architectures do some sort of compression and hierarchical metadata for depth buffers, which lets them do things like it improves the speed of like early out for early Z, so on. But those surfaces end up decompressing when you read them from a shader. So by denying shader resource, they can use a more efficient layout internally. I think that should be it for flags. Don't care about cross adapter, because multi-GPU is just a bad idea. And simultaneous access might come up, but only once we get into doing stuff with async compute, which we do not now. So, we're also not going to support MSAA. Which we may come back to in the future, because there's ways to like MSAA as an anti-aliasing solution is kind of meh, but having a different shading and sample rate is a really useful concept. And so you can do things like having variable rate shading in software based on, I guess, if you build a smaller MSAA texture, render to that with some combination of normal rendering and per sample shading, that lets you shade different objects at different frequencies, which can be useful, but it's not something we're going to get into. Because we are in DX12 and I'm on the Ampere GPU, we have actual VRS that we can get plugged in later, which isn't as high quality, but it's faster and doesn't require much work on my part. So someday. So I think that's all we need for texture creation. No, it isn't. We need to also actually create the resource. I'm just going to copy the call from up here. I'm going to do committed resources for now. In practice, you want to use place resources for a lot of things, but that requires that you do like manual sub-allocation, and I don't feel like doing that, so we're not going to. We're going to put this in the upload heap. We're going to put it in the default heap. Initial state. Let's see. I seem to recall this having constraints about what your initial state can be. Not the things in the default heap, okay. Need you right now in the doc. So we're going to pick an initial state based on usage flags that are passed in. So we will try in turn to create SRVs, or put it in SRV state, UAV state, and then DSV or RTV. Which are mutually exclusive, so we will succeed in putting it in some state. Start here. Let's start with SRV. that annoying that like pixel shader resources and non-pixel shader resources are a different state. That's get it, but that's awkward. A better approach here might be to make the user passing what the initial state is going to be. Won't bother right now, but and finally, result config, copy over the config that we created with. All right, did I forget anything? Doesn't seem like it. Texture destroy function. Need to handle different views. Yeah, it's not okay. Select user select. Um, Interesting. If you create an RTD for a buffer, that's interesting. Um, Now we're only going to handle the 2D texture case, and we're just going to assert in the default case, because I don't want to handle all of these cases right now. Dimension DX12 RT dimension D. Um, Obviously, we want to handle cases like rendering to a bitmap or rendering to an array layer, because those come up in various rendering algorithms a lot. But for the moment, we're going to be real simple about it and just say that we use the format the texture was created with, we use the dimensions the texture was created with, we always want to map 0 and array/0. Just because that's a good default for 90% of things, and it's just less work. Context, right? Target view. Okay, that was actually less work than I expected it to be. Cool. Now we do the same song and dance for stencil view. Okay, resource views. Should be very similar to the buffer version of this. So, sure. Format. again, um, SRVs in particular, we really do want to support like all sorts of different texture formats. But for the moment, we're only ever going to use these for like render target textures at the moment, so it should be fine to always assume they're 2D. We will make this better later. Leave those alone. So there's a lot of things that we want to support here with like binding a texture as a different format, or doing component swizzle, or binding a separate bitmaps. But at the moment, that's not important. Okay, it is 3 o'clock. I have stuff to do today, or I guess this afternoon. So we're going to leave off here. And we'll be back tomorrow, I think. And we will actually wire through our existing render target and depth buffer through the system, and maybe, just maybe, we might even get a start on like multi-pass renderer. Would that be cool? All right, so, God damn it. On that note, we're ending the stream.